Hello, welcome to another session. Today we are going to have a concept session. And the concept session, this is all going to be related to AC circuit. So you may have actually read somewhere that you have something called the capacitive reactance, inductive reactance, something called impedance, something called phase, and also frequency at which the circuit oscillates. So the AC circuit is a oscillating circuit, meaning current and voltage in the circuit oscillate, and they can oscillate at multiple frequencies, but we are going to talk about a single frequency. So frequency will be set by a source, which we'll call voltage source, V of t. So it will be set with a particular function. So we can usually write as V omega cosine omega t, and omega is angular frequency and it's related to the real frequency by this 2 pi f. Okay, and it is going to have two terminals. Usually we denote by like this, and this whole symbol is denoted like this, voltage source. So this source, you can connect a wire with some resistance, and of course, because that is a function of time, current will be a function of time, self-inductance will be, and because this is a wire made of a conductor like metal, they're going to be also capacitance. So I'm going to write the properties, right, the way I've been saying. So we can say, there's a resistance in the circuit, so it's a complete effective resistance in the circuit, whatever the value is. And then effective capacitance in the circuit is C, and effective inductance in the circuit, self-inductance in the circuit, which is going to be L. So this is like a series RLC circuit. It represents a whole bunch of circuits. You can have many circuits with one source, and you can write it like a RLC circuit, series RLC circuit. So this is the only one we need to study. So as a result, because of this a single branch, there's going to be only one current. So you will have some current I, which will go through the entire this thing. Okay. So we speak of EMF across this, EMF across this, EMF across this. So if you add up all the EMF, must be equal to that. So let's call it A, B, C, and D. So if although this is not a static circuit, if you go around the circuit doing the E dot dl, you can actually recast the whole thing. This thing will be like, I go from D to A, I pick up this. So it's going to be V0 cosine omega t. I go from here to here, I get a minus Ri. Go from here to here, I get a minus 1 over C t. Let's suppose the circuit was turned on at some time 0. So this is maybe 0 to t, and that will be whatever the current was coming in, dt prime. And then we have when I go across here, we'll have a self-inductance written like this. So this is the equation, which is kind of like there's an integral and differential. So this is like a pretty complicated equation, right, to solve for current. So when you solve for current, so current will have some magnitude I0, and it's going to have both cosine omega t and sine omega t. So we just call it I0c plus I0s sine omega t. And it will be like this. This equation will be like this for t much greater than L over R. This is the larger the resistance, shorter the damping, right? So this is so the full I will be a I where this thing is 0. So this is like a homogeneous I, and then this I. It turns out that when t is much greater than L over R, this part, L over R, IH of t becomes much less than I of t. And in that sense, we just kind of ignore this guy, and we just write like this. So this is also called a steady state solution. And this can also be written as a magnitude, some I0 cosine omega t plus some phase phi of the current. So you should be able to do this, and one way to find out all of these, find these guys, and then convert them to this. I'm not going to do all this math because we're not doing the math of this. You can do this by having this guy first converting this into I is dq over dt. So this equation just becomes just goes into v0 cosine omega t minus r dq dt minus 1 over cq minus L d square q dt square equal to 0. And try to solve this, and once you solve this, you get I from there. Okay. Another way to do it is just take a derivative of this. Take the derivative of this guy. Then it's minus omega v0 sine omega t minus r di dt minus 1 over c I of t minus L d square I dt square equal to 0. So this is a similar type of equation, except it's sine and it's cosine. And you may want to work out, and I'm just going to write the final answer, what it looks like. So the way we kind of represent these guys is, so you have at t equal to 0. So we write like this: at t equal to 0, we think of this as an angle, and think of them like a v0 cosine omega t is a v0 cosine omega t is a vector in this. So this is like some I hat direction, and this is some j hat direction. So this is I hat plus some j hat times 0. You know, this is we can write some arbitrary I hat j hat. This is not real I hat j hat in our real space. So we write this vector as like v0 and this angle theta. So when you write some vectors like this, then this vector, we call it a phasor notation. An actual function v0 cosine omega t is just this part. That's the v0 cosine omega t. So we put the omega t as an angle, and so omega t is called phase of this function, and then v0 is the amplitude of that function. V0 is amplitude of the function. So when we have something like I0 cosine omega t, we can actually write, so this is some I hat, and this is some j hat, and so say this was a omega t, and then this is phi I. Then this vector will be this vector will be I0 this way, and the entire angle starting from positive I hat direction all the way there, this entire angle will be omega t plus phi I. So this entire thing is the phase of I, and this thing is called phase constant. And you can put both of these in one place. So if phi I is positive, then putting these two in the same diagram kind of it doesn't make sense, right? This is voltage, this is current, but I'm gonna try to compare the phases, so I'm gonna have to have same diagram. So here is a diagram that I can say, okay, hey, this is the direction for V with angle omega t, and then let's, if phi I is this the phi I positive, then I will point in this direction, and this is I0 length. So this is this I say current with time, this angle is increasing, so both of them is going there, rotating. These vectors will be rotating with time because omega t will be increasing, right? And phi I remains constant. So their relationship remains the same, but they can rotate. And so this current is leading the voltage. So we say current leads voltage in this situation. Now, let me erase and to show you something else also. Now what if I had V in this, V was in the direction given by omega t. This is where the V was, but your I was actually maybe over here. So this is the direction of I, which means the phi. So you can see that this is the angle. This is not phi. This is minus phi I. So actually phi. So this whole angle will be omega t plus phi I. Let me erase all of that. So that's the phi I, right? So in this case, you can see that all this angle phi has to be modulo 2 pi. So I can write phi I is negative number. So this is phi I will be modulo 2 pi. So if this is the angle, say some theta, then phi I plus theta is 2 pi, right? And then phi I is just 2 pi minus theta. or you can actually simulate the same thing as phi I is being negative. So in this case, both of these vectors are rotating, but I is always behind V. So we say EMF or voltage leads I. And so this is the situation when you go in the current. This current comes this way. So we're kind of comparing across A and D what's going on. So the current, this current here that's going to go through, and the voltage they're not really in sync with each other necessarily. If phi I is 0, then they're in sync. But phi is not 0, they're not in sync. Okay? So that's for the entire circuit. That's what's going to happen. Now, I'm going to switch gear and talk about what happens across the resistor, across the capacitor, across the inductor. Okay? So just look at each of these things. Okay? Let me erase and just summarize. Okay, so what we noticed here is if current is equal to some current I0 and cosine omega t plus phi of the current, and so this is A to B, and V is V0 cosine omega t. So this is in the source, this is across the source. So then what we are going to have here is a couple of things I can, so this is at the source or across the source. So we already said if V is, we can represent this way. This is a phasor notation. So like a vector this way, and only the x, only this is it's representing, this phasor is representing V0 cosine omega t, and depending on the current being ahead or current being behind, current can be in this way or this way, because the phi being not correct in the appropriate direction, it's not the same direction as V. So a couple of things you can notice right away with just the source. Before I switch to each one of those components, with just the source, you can notice that the power, I didn't list over there, power of the source at the source will be just as a function of time, just gonna be I of t and V of t. So this is t. So this is not equal to just I0 times V0. This is I0 V0 cosine omega t times cosine omega t plus phi I. It's going to be like that, right? So it's going to vary with time, and you can already see that this is going to have two different components, cosine phi I times cosine square omega t, and then it's going to be I0 V0 sine phi I cosine omega t and sine omega t. It's going to be like that. So when you do a time average power, so time average, this will be half, and time average, this will be 0. So this will be half, and this could be 0. And you should convince yourself, we have talked about this in previous video, that if you have a cosine square omega t versus t, and then it's going like this, the time average will be half. But if you have something going up and down, up and down, up and down, then this time it will be 0. So you can actually do the calculation to show it. So this can just be half I0 V0 cosine phi I. And this phi I, if you have done previous calculation, you would know that this actually depends on R, L, and C values. Okay, so this depends on R, L, and C in the circuit. I'm not going to go in more detail, but this is in a previous video it has been addressed. Or if you want to see more of this, you can go to the physicsbootcamp.org. There's much more extensive discussion, and maybe some textbook that you have also has that discussion. Okay, so this is all about the source, and let's look at what happens across R. So this should be A to D, not B, A to D. So across R, well, what's the voltage drop? So the V, let's call it voltage drop across this will be V. This is of course the higher voltage than this if there's the directions going in. So VR of T equals to R I of T, and you can see that I of T and this this is I R of T. I'm going to write down IR. So if this is the case, whatever the voltage drop here is and the current, their phase has to be the same. So this means the phase of I when it across R is 0. So this VR in our case here, VR of T will simply be R I0 cosine omega T plus phi I. So if I write this guy V0R cosine omega T plus phi V, then this has to be equal to that, and because of that I can set this guy to be equal to 0. So this is the way. If you go out here, the phi I, this was the phi I for this case. So phi I is basically phase of I minus phase of V. So that's the definition for V of the source. So the way we have defined here the what we are claiming is the phase, whatever it is, this can be set to 0 because there's no difference between the two. There's no difference between the two. So if I took this guy as just omega T, then this guy will be just omega T, and that's why this is 0. Okay, let me erase a little bit. Okay, so if you plot these guys, just going to look like if this is the VR, voltage across the resistor, then the current is in the same direction. Current through the resistor is the same direction. This current is the same as the current through the entire circuit here. How about across this guy, across capacitor? So we have VC is just 1 over C integral I, is this the I t prime dt prime. So you can see that if I take a derivative of this, dvct dt is just 1 over c I of t. So to simplify, I'm going to call this guy through the capacitor. This is going through the capacitor. So if I say Vc of t is some new v, v0c, and let's call it cosine omega t. Just fix the phase 0 here because we want to have relative to it. So this guy is, say, in that direction, Vc at t. So that's the voltage across this guy's Vc of t. And if I plug in there, then I get a minus omega V0c sine omega t, and that's going to be 1 over c IC of t. So c comes out over there, and I want to absorb, I want to call minus cosine omega t, so I want to write minus sine omega t. So this is the positive part. So minus sine omega t into some kind of cosine omega t plus some angle phi. And you can see that if you expand this is going to be cosine omega t cosine phi minus sine omega t sine phi. Today my this pen is not really working very well. After today's video, I'm going to change this. So you can see the phi has to be pi over 2 for this to go to 0 and this to carry the minus sign. So this is pi over 2. So I have IC of t is omega c cosine omega t plus pi over 2. So you can see that this one is when this is omega t, and so another 90 degrees I have to go to get to IC of t. So the current, and the whole thing will be rotating like this, right? So the current actually leads. So the current leads voltage in terms across capacitor voltage by pi over 2 phase. Now I'm going to leave this as an exercise. Across inductor you have a VL T will be equal to L di dt, and you can see that this is exactly opposite the relationship. So here you can work out the math. You will say the current lags. So if you the VL of t is equal to some V0 L cosine omega t. So in this diagram, say you did this way, VL of t, then you are going to find that this is going to be IL of t will go exactly in the opposite direction. However, we have current the same, right? Not the voltages. So we want to look at the voltage here, and voltage here with respect to the current. Try this diagram, this is the current, how that will turn out. Let's talk about that now. Sorry, I forgot to actually do this part, turning on the video, because I paused it. So I'm going to, this is with respect to the, I picked the voltages in the same direction, but I want to, because the same current goes through all of this, so I want to do with respect to overall current phasor. So I want to draw a diagram, because that's normally how people draw these diagrams. So remember, this x component is the only thing I want, and the y component will just ignore in the phasor diagram. Okay, so let's see. This is the current, overall current, and this angle is omega t plus phi I in our case. Could be any angle, but we just want to write with respect to this. So first, the voltage across here is going to be in the same phase direction as the current, because across the resistor is the same phase. Whatever current going through that has this in terms of oscillation is exactly oscillating exactly same way and following it. Okay, so over here we saw that when it came to the capacitor part, current was leading the capacitor. So current is here, then the voltage across the capacitor will be 90 degrees behind it, just like over here. And the current lags when it's rotating. When the phasor rotating, current is behind the voltage, the VL. So the current is here, then the voltage will be ahead over here. It can be different value depending on the L value and the omega. Okay, so VL is like that. So we have these three phasors which represent what's going on in this circuit. And so in this circuit, you can say phasor-wise, phasors are like pseudo vectors, because we're only looking at the x component when we do the dynamic. So V overall, so V of the source is equal to V dropped across R as a vector, as this vector, the phasor vector, plus V dropped across capacitor vector, plus V dropped across L vector. That's pretty cool, actually. We're only interested in the x component of this vector, but we can very compactly write that equation, differential equation, that comes up in the analysis of this circuit. Okay, so now I want to go back to this reactances. So in the capacitor, we saw that with capacitor we saw that IC is equals to omega C cosine omega t plus pi over 2, and omega C must be, there's a V0 here, V0. So if let's take omega C on this side, 1 over omega C. So other than this time part, ignoring this part, so this is like a voltage and this is like a current, so this is like a resistance. So there is a name for this thing which has a unit of resistance. This has the unit of resistance, and this is what is called capacitive reactance. So this is reactance. Okay, so when we go over here, we're going to find that omega L IL is V0 cosine omega t minus pi over 2. We're going to find something like that. Okay, so now the resistance is this part is like a resistance, and so this is instead of calling it a resistance, we call it inductive reactance. So here and this whole thing is like a voltage, right? So this is the voltage across this scale. So this will be like a VL, and this will be other one like a VC. So the length of this thing will be 1 over omega c, 1 over omega c, and this length will be omega L, and this length will be R. So you can see the in terms of vector way, there can be so-called net resistance in this circuit, which goes by the name here impedance. This is not the full definition of impedance, but we will use this definition, usually denoted by letter Z, and which is going to be Z square will be R square plus omega L minus 1 over omega C square. So impedance squared will be defined as this for this circuit. A better analysis system is uses takes you into complex analysis, which captures all of this angle in a very nice way, in a better notation, but a lot of people don't see it till you get further in physics. Okay, so I am going to stop here. This is a lot of conceptual things we discussed. Next thing to do is move on, and we're going to talk about transformers, mutual inductance, how to write equation of motion for current in the 2 branches of a transformer. Okay, so we'll see you in another video. Bye.